Welcome back to Mr. Hassan's Maths channel. I'm answering question number 7 from the January 2018 International A-Level Statistics S1 paper. This is from Edexcel. Now, this question is about normal distribution, and one of the viewers has asked me to make a video going into a bit more detail in normal distribution. In fact, he asked me to make a video just explaining the whole topic. I don't normally do that, but what I do like to do is to try to explain topics such that people who have not understood them very well from the basics, they can pick it up from me answering the question. So I guess in this topic I'm going to try to explain it right from the basics. So I might go into a bit more detail than some of you require for this question, but that's one of the reasons why I make these videos, to help students who have some issues with certain topics to understand them from the basics. So first of all, what does it mean by normally distributed? Right, first, let's go back right to the beginning of what it means. Now, you have different types of distribution when you, for example, when you're drawing a histogram, where you have some data. For example, in this case, the weights of a particular gorilla. All right, so you've got some data where you have, adult, for example, gorillas from that breed, and we've measured their weights. Okay, we've measured their weights, and we've made a frequency table, collected their weights into groups, and we have, from the frequency table, we've worked out the mean and the standard deviation of the weights of those gorillas. Right, now there's different types of distribution that could occur when you collect data. One of them is where you can have data which is positively skewed, one negatively skewed, and one symmetrical. Okay, so let's have a look at these different types of distributions that you could possibly have. So you could have something like this where the you could say that the data is concentrated such that the lower side of the values contain more of the data. The data is more concentrated on the lower side of the values. Or you can have negative skew, which is opposite, where most of the data is concentrated in the higher values. So they're kind of lopsided, the histograms. All right, here you could say that the mode is going to be a value less than the median, which is going to be less than the mean. Here the opposite will happen. The mode will be the higher value, and the below that would be the median, and less than that would be the mean. That's positive and negative skew. Now, when you have data which is symmetrical, where it's basically evenly spread from the middle, like this, okay, the mode and the median and the mean are all the same value, right in the middle of the data. Okay, they're all equal to each other. That's symmetrical data. This is what is called normal distribution. When they say normal distribution, this is what we are referring to. This is not normal distribution. This is what we call normal distribution. And most naturally occurring things, like weights of, for example, this case, gorillas, heights of people, the heights of plants, whatever. All these naturally occurring things, IQs, they normally have a normal distribution. All right. So that's the first thing. Okay, so that's the first thing. What normal distribution means is when the data is kind of symmetrical, you could say. All right. Spread out evenly from the middle of the data. So this is normal distribution. Now, if we were to take the midpoint of each of these bars of this histogram and join them together with a curve, we would end up with a curve that looks something like this. Okay, it's like a bell-shaped curve, right? So that's just like when you join them together, you end up with this bell-shaped curve. All right. That's a normal distribution curve, basically, right? So that's where that curve comes from. That's a normal distribution curve. Let me go back to that. Now, supposing in this, for example, in a histogram, we want to work out the proportion of, the total number of, entries which have a, for example, supposing this was to do with the heights or the weights of the gorillas. Say this was, for example, we'll say this is about the weights of newborn babies, for example, and this will say between 4 and 5 kilograms. Just say, okay, so this bar represents between 4 to 5 kilograms. Okay, the weight of a newborn baby. All right. If we found the area of this bar, that would tell us the number of newborn babies that were born between 4 and 5 kilograms. That's what a histogram, the area of the bar represents the frequency. And if we took the area of this bar divided by the whole area of the whole shape, that would give us the proportion of the babies in this survey, which were between 4 and 5 kilograms. So the area of the bars, or the bar in that you're looking for, those areas gives us an indication of the number of entries in that region, and dividing that area by the whole area of the whole thing tells you the proportion that belongs to that particular category, right? So when we're dealing with normal distribution, okay, what we're doing is, oops, what's happening here? When we're dealing with normal distribution, what we're doing is we are finding the proportion, okay, within a certain category. So in this case here, it says the weights G of a particular breed of gorilla are normally distributed, so they're such that they're normally distributed, so that we know that their distribution is of this shape, with a mean of 180. Okay, so the mean is the one right in the middle, that's 180 kilograms. Okay, this is for your G values, and a standard deviation of 15. Okay, standard deviation is a measure of how spread out things are from the mean. So the standard deviation is 15. So here we write 15 and we put squared, because this number here is the variance, which again is a measure of the spread of the data. It's just the square of the standard deviation. All right, so we want to find the proportion of these gorillas whose weights exceed 174 kilograms. Now, 180 kilograms is here. 174 kilograms is less than the mean, so it's going to be somewhere over here. Okay, so what we need to do here, just say that's 174 kilograms. Okay, 174. We are looking for the area which is to the right of this. We were looking for the proportion. Okay, we're looking for the area of all the bars to the right of this divided by the whole thing. That's what we're looking for. If we find the area of all the bars to the right of 174 until the end, and divided that area by the area of the whole thing, we would get the proportion of gorillas whose weights exceed 174 kilograms. Right? That's what we would do. That's what would happen if we did that. Now, what we have is we have something that helps us to do this, okay, which we can do. We can access by what's called standardizing these values, okay, because we have a table. Instead of finding the area for this particular, curve, where the standard deviation is 15 and the mean is 180. Okay, we have a table of values here, which tells us, okay, the area. Okay, so this table of values on this side here tells you the area, okay, under the curve for different values of Z. So for this value here, for example here. So this is the area to the left of this Z value. Right now, this value on the axis, the horizontal axis. Now, this data here is for the situation when the mean is equal to 0 and the standard deviation is equal to 1. That's this case. This is the case that we're dealing with. So this is these values are, for example, if this is say 2, that means this is for when the standard deviation is 2 and the mean is 0. These numbers apply. So if I wanted to find the area, okay, to the left of this 2, that would be 0.9772. So this area here is 0.9772, and the area of the whole thing, underneath all of this is equal to 1. So this would be the proportion of items which has a which it was basically less than 2 standard deviations above the mean, right? So that's what that refers to here. So this is referring to data when it is, you can say, when it has a standard deviation of 1 and it has a mean of 0. When it has a mean of 0. Okay, that's what this will refer to. Okay, so what we can do here is we can do something to these numbers such that we make the standard deviation 1 and the mean 0. We standardize these values. We basically find out how many standard deviations, in this case below the mean, will this number be. And the way to do that, to standardize the score, Z is called the standardized score. You take your value that you're trying to standardize and you subtract from it the mean, and then you divide that by the standard deviation, and that will give you your standardized score. So if I want to find the proportion, you could say the probability that the weight of the gorilla, which is G, is less than, or is greater than, in this case, it's greater than 174 kilograms. What I can do is I can say that's the same as saying the probability that Z is greater than, and then I can standardize this score. So it's 174 minus the mean, which is 180, divided by the standard deviation, which is 15. Okay, so that will be the same as saying the probability that Z is greater than, so we can take our calculator and we can say 174 take away 180 divided by 15. That gives us minus 2.5, which is minus 0.4. So we can say here, just make a bit of space here, we can say here that the standardized value, the Z value of this is 0, of course, when we made the mean 0, and now the standard deviation is negative. I mean, it's 0.4 standard deviations below the mean. Okay, so now I need to find the area which is to the right of this value, minus 0.4. Now, unfortunately, we don't have a 0.4, negative 0.4 here. Okay, the Z values we have only start from the positive side. So the Z values start from 0 and they go that way. Right? So we don't have negative 0.4 for Z. This is the Z axis. We don't have that in our tables. So what do we do to solve that situation? Well, we know that this is symmetrical. And I know that if 0.4 is here, then there will be over here minus 0.4. Okay, so this and this are like such that it causes some sort of symmetry. So if I'm trying to find the area to the left of this all the way back to the beginning, which is what I'm looking for, well, that's the same area as to the right of this all the way to the beginning. So I'm actually, that's what I'm looking for. I'm looking for the area to the right of this. It's the same as the area to the left of this. Okay, so if I can find the area to the left of 0.4, if I go to 0.4 and I find the area to the left of 0.4, which is this area here, that's the same as the area to the right of negative 0.4, which is what I'm looking for. So all I have to do is go to 0.4, and this is the area to the left of 0.4, and this is what I'm looking for. This is going to be my answer, 0.6555. That will be the percentage or the proportion of the gorillas who have a weight greater than what we were looking for. So let's just come back here. So basically, what we can say that this is the same as saying the probability that Z is less than 0.4, which our table gave us as 0.6554. 0.6554. 6554. Okay, so that is, so therefore we can say the probability that the gorilla has a greater weight greater than 174 kilograms is equal to 0.655 to 3SF, and there's our answer for part A. All right, so I hope that was a bit clear, explaining from the beginning. And then it says, find to one decimal place the value of K such that the probability that the gorilla's weight is between K and 174 is 0.3196. Okay, so now we can do something similar. We know already that 174 is over here. Okay, we know 174 is over there. And we also know that this is, that's 174. And we want to find the probability that the gorilla's weight is between K and 174. So K is going to be somewhere over here. K is going to be somewhere over here. It's going to be less than 174, of course. So this is K. So we're told that the area here is 0.3196. So that's the area there. Now we don't want to find what the value of K is. All right, so now what I can do is the following. I can flip this and think of this, because as we said, this is negative 0.4, and this is going to be a negative value, right? This is 0 in terms, this is G and this is Z. So if we kind of flip this around so that we think of it from the positive side, okay, so I'm thinking now of taking this as 0.4 over here, and then the K value would be over there, right? So this would be our positive 0.4, and this would be our K value, all right, that we're looking, but this will be the opposite sign of what we have there. So this is like the you can say, you know, K dash or K1, right? So we've got here, and this area is the same as that area because it's symmetrical. So this area is 0.3196. That's the area there. Now I know that the area that's less than 0.4, this area over here, let me just make that thinner. I know that the area from there all the way to 0.4, we already worked out that area in the last part of the question. We worked out that that area there is 0.6554. So this area is 0.6554. So we can say that the probability that Z is less than K, the probability that Z is less than K is equal to 0.6554 plus 0.3196. Okay, it's the whole area below there, right? And whatever K value we get here, we're going to have to find the negative value for this. That will be on the negative side, and then we can work out what the actual value is in terms of its, you know, the actual value. So I'm going to call this, actually, I won't call this K, I'll call this GK. Okay, GK. This is G, and Z is down here. Okay, so we know that this is, you know, above me. So this is going to be, I'll call it GK, right? So let's just add those together. So we have 0.6554 plus 0.3196. Now that gives us 0.975. That's 0.975. So we will find the probability that Z less than GK is equal to 0.95. All right. So we're trying to find what the value of Z is for that, right? Okay. So what we can do here is we can use we can find the value of, we can find what ZK is now, right? So we can use the curve. So we've got two options here. First of all, we could go to what we see. We don't have 0.975. No, we do, in fact, we do have 0.975. What we're talking about. So 0.975, okay, is here. All right, and the Z value for that is 1.96. So this is the area to the left of this Z value. Here we know the area, we're looking for the Z value, right? So now we know the area and we're looking for the Z value, and there we have the area exactly mentioned in this table as 0.975 is exactly mentioned as that value. So we can use that quite easily. Okay, so we have the area 0.975 exactly. All right, and where is it? Here we are, and there we have the corresponding Z value for that. Okay, 1.96. That's one option. The other option is to use this table over here. And normally you would use this table over here in a case where you know the exact values. And if we're looking for the probability that Z is less than 0.975, well, that's the same as the probability that Z is greater than 1 minus 0.975. And if you do 1 minus 0.975, you get 1 over 40, which is 0.025. 0.025. And this table on the top here has probability values. Okay. Sorry. Z is less than K is equal to 0.975. So the probability that Z is greater than K is equal to 0.025. Sorry about that. That's okay. I meant to write that. I wrote something else. Okay. So the probability that Z is less than the K value is 0.975 is the same. Okay. Basically, you know, it's the same as saying the probability of Z is greater than K is 0.025. You know, the same value of K will give both of these, right? Okay, because they add up to 1. So the table over here tells us the first column is the probability, the area, and the second column is the Z value, for which that is the area to the right of this Z value. So here, if we look at 0.025, we see we have it over here. Okay, and this is the value of Z, for which that's the area to the right of it. As you can see, you get the same value of Z, 1.96. So in either case, both tables would normally be okay in this case, in this particular case. But normally you would use this table if you have these exact values of P, because it gives more precise values of Z. In this case, the value of Z is the same accuracy. I think it's the only one out of all of these that gives you the same accuracy. So here it wouldn't really matter which table you use, but generally you would use this table if you find these kind of exact values. So when you get something like that, it says 0.0975, subtract from 1 and see what you get. If that value of the area of P is in this table, then it's better to use this table here. All right, and you're looking for this is the value of Z, for which that's the area to the right of it. So we know that our value of Z is definitely 1.96, whichever way we did it. So we end up with 1.96 is our value of Z. So this is 1.96. Okay, so that's positive. So our value that we're looking for here, okay, the Z value that we're looking for here is negative 1.96. Okay, so we can say that the Z value that we're looking for, okay, for our K is negative 1.96. So now we can unstandardize the score. Remember the standardized formula, Z equals X minus the mean over the standard deviation. So here we have negative 1.96 equals the score, which we're going to be finding what it is now, minus the mean, which was 180, over the standard deviation, which was 15. Okay, 180 and 15, that's right. Okay, so now we can say therefore X is going to be 180 plus, or you can say minus 180 minus 1.96 times 15. Okay, so it's 15 times that plus 180, that's right. So X is going to be 180 minus 1.96 times 15. Okay, that gives us 150.6. 150.6, okay, kilograms. All right, so that is the value of K. I'll say therefore K is equal to 150.6 kilograms to one decimal place. Okay, so there's your answer for number 7, part B. All right, now for part C, the weights B of a particular breed of buffalo are normally distributed, so B are such that they're normally distributed with a mean of 216 kilograms and a standard deviation of 30 kilograms. Given that the probability that the G is greater than W is equal to the probability that B is less than W, and both of them are equal to the same probability P, right? So we know that G is normally distributed with a mean of 180 and a standard deviation of 15. All right, so this is the information we have. So they're saying the probability that G is greater than W is equal to the probability that B is less than W. All right, so we're going to try and find what W and P is. Okay, so let me just take, I'll get 2 of these this time. And I'll compare them. One for B, one for G. One for the buffalo, one for the gorilla. Right? So now, say this is the buffalo and this is the gorilla. The buffalo has a mean of 216. The gorilla has a mean of 180. Okay, and they're telling us that there's a value W where the probability that the gorilla has a weight greater than that is the same as that probability that the buffalo has a weight less than that. Okay, so those W values have to be the same. So what we can say is that for the gorilla, the probability that the weight is greater than that value, okay, so that means for the gorilla, it's going to be something which is going to be over on this side here. Okay, and for the buffalo, it's going to be something on this side here. Our W is going to be over here for the gorilla and here for the buffalo. Okay, because the probability that the gorilla has a weight greater than that is going to be equal to the probability that the buffalo has a weight less than that. All right, so it has to be such that these two areas are the same. This area here is the same as the area there. Okay, so it must be that it's in this case here because the buffalo has a bigger mean, right? So the area for the buffalo being less than that value has to be equal to the probability that the gorilla is more than that value. So it's going to be something like this. Okay, that's W, that's W. So this value of W and this value of W, okay, they are going to have basically the standardized values for these. Okay, this is going to be, for example, this will be minus the value of Z that this is. I call this ZW. This will be the negative version of this because those areas have to be the same. Okay, so if we look at for the gorilla, okay, let's look at for the buffalo first. Let's look at for the buffalo first. We can say that you've got ZW, okay, is going to be the value of W minus 216 over 30. And for the gorilla, we're going to have the ZW value is going to be equal to W minus 180 over 15. Right? Now, these values are going to be opposite values to each other. They're going to be opposite signs. So I could say, for example, that W minus 216 over 30, the Z value we get for this is going to be equal to the opposite sign for the other one, W minus 180 over 15. They have to have opposite signs. So I can try to find what W is now from this. If I multiply both sides by 30, then that will get rid of the fraction. I'll have W minus 216 equals, I'll have minus 2 times W minus 180. Because I've multiplied that by 30, they get 2, so I have minus 2 times that. So I have W minus 216 equals minus 2W plus 360. So I'll have W plus 2W, which is 3W, equals 360 plus 216. So 3W equals, that's going to be 576. So W equals 576 divided by 3. 576 divided by 3, which gives us 192. So W is 192 kilograms. So we know that this is 192, that makes sense. This is 192, that makes sense. That's less than the mean, that's more than the mean, right? So now we can work out what the value of P is. We want to find the area over here, this area over here, okay, or this area over here. We could say, let's use this value. Let's standardize this W value. So we can say that we got Z equals X minus the mean over the standard deviation. So if we take this 192, if we take 192 minus 180 over 15. I've taken it from the side from the gorilla because it's on the positive side. So the Z value for that is going to be 192 minus 180 over 15. Let's do it like this. 192 minus 180 divided by 15. That gives us 4/5, which is 0.8. Okay, so the Z value for this is 0.8. So we're looking for the probability that Z is greater than 0.8. Okay, the probability that Z is greater than 0.8, which is the same as 1 minus the probability that Z is less than 0.8. Okay, because I want to find this area over here. Now the table that we're going to use, the big table, only has the area to the left of those Z values. We have this value here, which is we will have to find what the area is to the right of it. So if I find the area to the left of it, subtract from 1 because the whole thing is equal to 1, I found the area I want. So that's going to be, if I go to 0.8 on my table, let's go to 0.8. Okay, you see it's 0.7781. 0.7781. Okay, so that's what we need to go to over here. 0.7881. So it's 1 minus, whoops. It's 1 minus 0.7881. Okay, I just want to make sure because 7881. Okay. All right. So the answer is going to be 1 minus 0.7881. That gives us 0.2119. 0.2119. Okay, so it says so that there's the value of W, so that's part 1 done. Okay, that's the answer to part 1. And to part 2, we can say P is equal to 0.212 to 3SF. So there's part 1 and there's part 2. Okay, that's kilograms. And there we have it. There's the answer to this question, question number 7 from this January 2018 paper. I hope that was clear. Thank you for watching. Other questions from this particular paper can be found in the playlist that will be shown over here. The end, other questions from the topic of normal distribution from S1 can be found in the playlist over here. You can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.